Welcome to the deep dive. I'm your host, and today, I want you to imagine for a second that you are trying to organize your kitchen.
Oh, I'm your resident expert, and I can already tell this is going to be about over-optimizing things.
You know it. So, you want to cook your absolute favorite meal as fast as humanly possible.
Right.
You optimize everything. Like, you put the pans exactly arm's length away, you line up all the utensils in order of use.
Everything has its place.
Exactly. You meticulously reorganize your spice rack so you can just grab and pour without even looking. I mean, it is a masterpiece of efficiency.
Sounds perfect. So what goes wrong?
Well, in the blur of all that hyper-optimization, you accidentally label the salt jar as sugar.
Oh, no.
Yeah, you start cooking, your movements are faster than ever, the process is incredibly smooth, and your final dish comes out of the oven in record time.
But the moment you take a bite, it is completely ruined.
Completely ruined. Because you just dumped, a heaping cup of salt right into your dessert.
Which is a flawlessly executed process based on a fundamentally flawed assumption.
Right?
I mean, the system did exactly what it was optimized to do, but it lacked the specific awareness to know that what it was doing was disastrous.
And today on the deep dive, we are looking at a developer's log from July 4th, 2026, where a programmer named Ang made this exact same optimization mistake.
Yeah, the log is titled Notes on Haskell-Programming Part 178, Fixing the Full-Width Space Mapping Bug.
So we are going to unpack the anatomy of a software bug. We'll explore that tension between, making code run incredibly fast and making sure it actually does what it's supposed to do.
It's a tricky balance.
It really is. We're going to dive deep into the invisible mechanics of digital character mapping. And we'll discover how a developer's attempt to fix the reading layout of Chinese novels reveals a much broader, honestly fascinating lesson about how our data is constantly being processed, destroyed, and reconstructed behind the scenes.
I mean, the premise sounds highly specialized, I know, but the mechanics of this specific error really expose the foundational rules of how digital systems interpret human culture.
Yeah, absolutely.
Like a microscopic mathematical error in a single line of code spiraled into this bizarre formatting glitch that just ruined the reading experience for users.
To understand how that happened, we really have to look at the trap of optimization.
Right, because Ang's starting point was what programmers call a refactoring of their code.
They were cleaning house.
Exactly. And by all standard metrics, this refactoring was a massive success. The notes point out that this new version reduced the total lines of code, and it actually resulted in much faster mapping.
It was leaner. It was meaner.
Yeah, but this beautiful optimization introduced a bug into the mapping process that Ang describes as both significant and common.
Which raises that classic programmer's dilemma, right? Isn't it ironic that the code was technically running faster and looked much cleaner, but was fundamentally broken in what it was supposed to do?
It really is.
It's like building a faster car that only drives in reverse.
That's the paradox you see all the time in system design. Computers, they love broad, uniform rules. If you tell a system to apply the exact same mathematical operation to every single piece of data it encounters, the system will process that data incredibly fast.
Broad rules equal speed.
Exactly. Broad rules equal speed. The danger, though, is that applying broad, sweeping rules blinds the system to necessary exceptions.
And the real world is built entirely on exceptions.
Oh, absolutely.
So if broad rules are the problem, what was the broad rule Ang was actually trying to enforce here? Like, what was the code trying to do?
Well, the code's main job was character mapping. Specifically, it was supposed to map what we call single-width characters to double-width characters.
Okay, let's break that down.
Sure. So in digital text encoding, the standard characters you type on an English keyboard, letters, numbers, basic punctuation, those are considered single-width.
They're narrow.
Right, they are narrow. But in many East Asian languages, including Chinese, Japanese, and Korean, characters are typically wider. They're designed to take up a uniform kind of square space.
A grid layout.
Exactly. So for visual consistency on a screen, systems often need to convert those narrow, single-width English characters or punctuation marks into double-width or full-width versions.
That way everything aligns perfectly within that grid-like layout.
You got it.
Okay, but underneath the hood, a computer doesn't actually see a letter A or a blank space, right? It just sees a number.
Yeah, basically a digital coordinate.
Right, a digital coordinate. So Aang wanted to change a whole block of single-width characters into double-width characters. And to do that, the optimized code applied a uniform mathematical operation.
It took a sequential block of characters, starting from the space character all the way up to the tilde character, and just added a specific hex value to every single one of them.
And that value was 0x face.
Right, 0xe0. To visualize why this math works, you have to think of the Unicode system, which is the universal standard for encoding text, as this giant digital apartment building.
Okay, I like this analogy.
So the standard English letters and characters live on the first floor. If you want the wide East Asian compatible versions of those exact same characters, you don't build a new building. You just go to a higher floor.
Oh, that makes sense.
Yeah, the architects of this digital building assigned the wide characters to a floor exactly 0x feet steps higher.
So adding that specific hex value acts as like a perfect mathematical elevator.
Exactly. It takes a standard narrow A directly up to the apartment belonging to the wide A. It is a highly elegant mathematical shortcut.
Because instead of writing hundreds of separate instructions for every single letter.
You just select the whole block of residents and send them all up 0x feet floors at once.
Wait, but is it actually elegant if it's blindly applying this math to everything?
Well, that's the catch.
Because the blank space character was at the very beginning of that sequential block, right? So it got forced into that same elevator.
It sure did.
And adding that value to a blank space didn't create a wider double-width blank space. It shot the space up to a completely random apartment and mapped it to an unexpected character known as 3020. I mean, that sounds like lazy programming, not elegant math.
It's the dark side of efficiency, honestly.
Yeah.
The math itself is completely flawless, but the assumption that every character in that block follows the same architectural rules is flawed.
Because the space character is unique.
Right. When you take the space and force it up those 0x feet floors, it doesn't land in the apartment reserved for the wide space. It lands in apartment by 3020.
And part 3020 is absolutely not a space.
No, it's not.
It's the ideographic postal mark circle. Visually, it looks like a large, prominent, unbroken circle. A zero, essentially.
Yeah, it's a completely valid character in the Unicode system, often used in Japanese postal contexts, or sometimes as a symbol for zero.
But obviously not what you want when you hit the space bar.
Exactly. The issue is that the code should have mapped the original space to by 3000.
Okay, so a totally different coordinate.
Right. That specific coordinate is the correct ideographic space, which is the actual full-width space used in Chinese, Japanese, and Korean text. The mathematical shortcut missed the correct apartment by a significant margin.
So imagine trying to read a relaxing novel, but instead of the empty, quiet spaces between words or at the start of a paragraph, a rogue typewriter is just aggressively stamping a postal circle everywhere a space should be.
Just circles everywhere.
Yeah, circle, circle, circle. It would completely ruin the reading experience. It's so jarring.
It's a jarring visual error born entirely from the fact that the space character was treated as just another number in a sequence.
It was a victim of uniform optimization.
Exactly. It lacked the special treatment its function required.
But, code doesn't exist in a vacuum. It exists to serve human needs.
Right.
So why was this specific error stamping postal circles instead of spaces so catastrophic for Aang's particular use case?
To understand that, we have to look at what Aang was actually building.
Right, the novels. Aang's notes explain that the single-width space character is incredibly common in the Chinese novels this software is processing.
And these spaces are specifically used for paragraph indentation.
Which is fascinating, the formatting rule here, because to simulate the physical length of two double-width characters, which is the traditional paragraph indent,
Authors will typically just tap the space bar 4 times.
right, using 4 single-width spaces to fake the width of 2 full characters.
And this really highlights how digital systems are constantly forced to interpret and accommodate human behavior.
Yeah.
You have an author sitting at a keyboard, hitting the space bar 4 times, because they visually want the indent to look a certain way on the screen.
They're using a blunt digital tool to mimic a very specific physical typesetting tradition.
Exactly.
It's wild that in a world of complex Haskell programming, Unicode mapping, and hexadecimal math, the whole system basically broke down over the need to simulate physical formatting for a novel.
It really is wild.
It shows how our most advanced digital systems are still entirely tethered to very old reading habits. Like the software has to bend over backwards to make sure the digital page looks exactly like a printed page.
Because digital encoding has to perfectly translate those cultural nuances. It's not just about making sure a computer can store and transmit the data.
Right. It's about making sure the data feels natural to a human reader.
Exactly. So when that mathematical elevator failed and produced the postal mark circle, it didn't crash a server or corrupt a database.
No, it violated a cultural formatting expectation.
A failure in the math became a direct failure in user experience.
So how did Aang fix the math to save the user experience?
Well, they realized they had to break that perfect uniformity.
So they split the code logic into two distinct parts.
Yes. First, they pulled the single space completely out of the lineup. They explicitly wrote a new line of code mapping the single space directly to the correct full-width space.
To that by 3000 value.
Right. Then for the second part, they applied the uniform plus 0x feed offset only to the remaining characters.
So starting from the exclamation mark up to the tilde.
Exactly. They created a hard-coded exception for the space and then applied the broad rule to everything else.
I mean, it adds a line of code, and it might be fractionally slower than the hyper-optimized version.
But it's factually correct. It acknowledges that the space is fundamentally different from a letter or a punctuation mark.
Okay, so the math is fixed, the postal mark circle is gone, the correct full-width space is back.
Problem solved, right? The novels are going to indent beautifully.
You would think so, but here is where Aang's log reveals a massive structural plot twist.
Oh, wow, what happened?
Even though the mapping function works perfectly now, it still didn't fix the actual use case for the novel indentation.
Wait, really?
Yeah, the paragraphs were still not indenting properly.
But why?
The reason why is almost comical. Earlier in the software's process, during a stage that Aang calls the parsing phase, the code had already stripped out all leading and trailing whitespace from the text.
Wait, before the text even reached the character mapping stage where the postal circles were appearing?
Yes, the system had run a completely different operation designed to clean up the raw data. And the sole job of that cleanup operation was to aggressively delete any extra spaces at the beginnings or ends of lines.
Exactly.
Wait, so those 4 spaces the author carefully typed to create the indent, the exact spaces Aang just spent all this time perfectly mapping so they wouldn't turn into circles.
They didn't even exist at this point in the program.
A parser had already eaten them.
It had already eaten them.
Why even bother fixing the mapping bug if the data's already gone? Aang just spent hours troubleshooting and fixing a problem that didn't even matter to the final output.
I know, it sounds crazy. It is entirely logical to ask why you would fix a leaking pipe if the water to the house is already shut off.
Right.
But this touches on a fundamental concept in software architecture known as the separation of concerns.
Separation of concerns. Okay, how does that apply here?
You have to fix the mapping bug because the character mapping function is a core tool in the system's toolkit. Today, it's being used to process novels. Tomorrow, it might be used to format financial data or usernames or critical system commands.
Oh, I see.
If a core tool contains a mathematical error that randomly turns spaces into postal circles, it is a ticking time bomb.
So it does not matter that the parser stripped the spaces for this specific novel reading use case.
Not at all. Fixing the core function is vital so that it doesn't break other completely unrelated things down the line.
Because each independent piece of the system must do its specific job flawlessly, regardless of what the other pieces are doing.
Precisely.
You can't leave a broken hammer in the tool docs just because you happen to be working on a gluing project today.
That's a great way to put it.
That makes perfect sense for the health of the overall software. But it brings us right back to the primary goal of the deep dive.
Right.
If the original spaces typed by the author were deleted by the parser, how do the Chinese novels actually get their traditional indentation back?
Well, we have to look at Aang's final reconstructive solution. This is where the philosophy of handling data takes a fascinating turn.
Okay.
We move from data preservation to data sanitization.
Data sanitization. So Aang realizes that the spaces being deleted by the parser isn't an issue at all. In fact, it's a massive advantage.
Huge advantage.
Because the parsing phase cleanly stripped all the messy, unpredictable original white space, right? Like, some authors might type 3 spaces, some might type 5, some might use tabs.
Yeah, human input is messy. But now Aang has a perfectly blank slate at the start of every single paragraph.
The parser removed the human imprecision. It standardized the data by destroying the formatting.
Exactly.
So instead of trying to preserve and translate the author's original messy keystrokes through the entire complex pipeline of the software,
Aang decides to bypass the original keystrokes entirely.
the final fix is incredibly simple, isn't it?
It really is. Ang's code explicitly adds the correct double width of spaces back into the paragraphs for indentation at the very end of the process.
Right before the user sees the text.
Yep. It's counterintuitive because we usually think of digital systems as these perfect memory banks designed to preserve exactly what we put into them.
But sometimes trying to perfectly preserve and translate messy, human-inputted data is the exact wrong approach.
Oh, definitely. Hitting the spacebar 4 times is a human hack.
Mm.
You try to hold on to that hack and push it through layers of complex system architecture, things will break.
It's often much more efficient and much safer to completely destroy the original formatting, like strip the data down to its raw structural information.
And then artificially reconstruct the correct formatting later according to strict, predictable system rules.
It's kind of like buying an old rickety house that's leaning to one side. Instead of trying to reinforce every single crooked beam and prop up every leaning wall to make it straight, you just tear the house down to the raw foundation.
Right, and build a perfectly straight, brand new house on top of it.
You destroy the original structure to ensure the final result is perfect.
Ang recognized that the intent of the formatting, the visual paragraph indent, was what actually mattered to the reader.
The actual keystrokes the author used to achieve that intent were irrelevant.
And frankly, a liability. By erasing those physical keystrokes and programming the core intent directly into the final output stage, the system becomes incredibly robust.
Wow. We started with a developer simply trying to make their code run faster and leaner.
Yeah, that hyper-optimization trapped him.
It uniformly applied a mathematical elevator to a simple space character, which accidentally launched every space into an apartment occupied by an ideographic postal mark circle.
A very strange glitch.
Very strange. And then we explored the traditional physical formatting of Chinese novels, learning how our digital systems are constantly forced to accommodate our physical reading habits.
And finally, we discovered the structural plot twist.
That the parser had eaten the spaces anyway.
Right?
And that realization led us to understand that the best way to handle digital formatting is sometimes to intentionally erase it and build it back from scratch.
It is a remarkable journey from a single line of hexadecimal math to a broad philosophy of data management.
It really illustrates just how interconnected every single layer of a digital system truly is.
And how a tiny oversight in one corner of the architecture can expose the cultural assumptions built into the whole machine.
Consider how Ang realized it was easier to completely erase the original formatting and artificially add the correct double-width spaces back later rather than carefully translating the author's original keystrokes.
Yeah,
It makes you wonder about the text you consume every single day.
absolutely.
Like when you read a beautifully formatted digital book or a perfectly aligned article on your phone, how much of the author's original digital manuscript was actually preserved?
Probably less than you think.
And how much of it was quietly destroyed, sanitized, and artificially reconstructed by a developer's invisible code just to make it look right to you? Thank you for joining us on this deep dive.